If there's any questions at all, feel free to hop off mute or pop it in the chat. Either is fine. Today's class we're going to be looking at transformations from the ground up. So it's around this time when Unit 1 and 2 is starting to look at transformations. So we're basically going to just revise and cover all the fundamentals for it. So to the screen share. I'm going to teach it in a way where how the textbook teaches transformations, because I believe it's probably the better way of going about it. I do notice that a lot of schools, mine included when I studied, will teach it a slightly different way, which is more about substituting values into the functions in general, which is fine. It works perfectly fine. It's actually a faster method of going about things, but it's a little bit less intuitive to understand exactly what's going on and why what's going on is going on in that way. So the method that we're going to have a look at today is going to be in this sort of so-called point notation, where rather than think about things in terms of functions, we're thinking about the individual x and y coordinates on that curve and mapping them to some new x and y coordinate. Because that's all a transformation really does, right? It's something to change the shape of the graph in some way. And by changing the shape of the graph, you're effectively moving the x and y coordinates of that graph to some new location. This is the overall procedure as to how we apply transformations using this approach. You don't have to have that memorized just yet. We're going to have a look at a bunch of examples on how you can do that. The first kind of transformation that we'll have a look at are the dilations. So dilations are all about stretching a function in a certain direction, either in the y direction or in the x direction, horizontally or vertically. The way dilations appear in this sort of notation is to apply them as a multiplication on either the x or the y, depending on what direction you want to stretch towards. In this case, we're looking at a dilation along the y-axis, so it is the y variable that's going to get that dilation factor of a. A little bit about terminology here. There's a couple of ways that you can describe a dilation in a particular direction. You can describe it as either along the axes that you're talking about, in which case it's stretching in that direction, or from or away from the opposite axes. Now, unfortunately, this is the one the book defaults to every single time, and it's also the one that I see most often in the exam. So I've got both in here because both are valid, but worth pointing out, this is the one that you'll see the most. I just wanted to describe like what that way of expressing it actually means. You can think of this as moving away from the axis rather than going in that direction. Or in other words, just opposites. Both of these are referring to the same thing. It is applying the multiplication factor of a, the dilation factor, to the y variable. Now, how do we actually do that? First things first, we're going to convert our point form notation into a couple of equations that describe what's going from x to x and what's going from y to y. So basically, the left-hand coordinate of this one is now going to be equal to the left-hand coordinate of this one. Wherever you're starting is going to get x. Wherever you're going is going to get the x dash. So in other words, the new x is equal to the old x. Nothing's changed here. There's no factor that's been applied. And the new y is going to be a multiplied by y. All right, it's the coefficient applied to it. All this says is the new y is going to get ay. From there, rearranging in terms of x and y, this is stuff you guys have already done before, right? Just get the x on its own and the y on its own in both of those equations. Nothing really has to be done here. Something has to be done here, just dividing the a. Then, whatever the function is that you're trying to apply it to, simply replace every instance of y with what it equals and every instance of x with what it equals. You're just doing two substitutions. When you do that substitution, we will remove any of the dashes in there. Those dashes are simply for us to understand where we're starting and where we're going. They don't actually make it through when you actually put that substitution in there. So we have some generic y equals f of x. y is equal to y dash over a, so we're going to replace that y with y over a. X is equal to x dash, so nothing's changing there, it's just x. This is no longer in a typical function sort of notation, so we're just going to do a quick rearranging to make sure that we still got y on its own, just like every other function that we look at. So all said and done, whenever you do a dilation along the y-axis, or from the x-axis, this is the end result after going through the procedure. It is just whatever the function is, you multiply the entire function by that coefficient. This is going to seem excessive, an excessive amount of steps, given that we're just getting to here. This procedure is more so teaching you why this is the way it is, and has more applications when you're trying to do multiple sequences of transformations rather than just individual ones. Because this is excessive for a single transformation, less excessive if it's when you're doing multiple. Any questions about how that's worked so far? Cool. Here's a quick example. So we're trying to apply a dilation factor of 2 from the x-axis for the square root function. The dilation factor is 2, and it's going away from the x-axis, or in other words, in the y direction, toward the y. So the dilation factor of 2 is going to go on the y. The only part here that matters is that y dash is now equal to 2 times y. Step 2, do your rearranging. Step 3, replace each x and y with what they are now equal to. The only thing that's different is going to be the y is now going to become y over 2, and then finally get the y back on its own. We've now effectively applied the transformation. The exact same thing exists for dilations in the x direction, so either along the x or from the y. Literally all we're doing is replacing the a on the x variable rather than on the y variable. At least as far as the steps that we follow, that's the only difference. One thing worth pointing out though, oddly enough, is when all is said and done, when you've actually rearranged everything to its final position, what we'll notice is that when it gets substituted into the function, because there's no additional step of trying to get this y back on its own, dilations that are in the x direction end up appearing as divisions in our function. So any f of x divided by a, whatever the divisor is the factor. Whereas in this case, it was a multiplier. Both of them were referring to the same thing, a dilation factor. But in this case, it was a multiplication. In this case, it ended up being as a division. So this is less important for the steps of just shoving transformations into a function. More so important when you're looking at your function and trying to use that to determine what transformations you have. So it's good to know both, how to put transformations into the function and how to look at the function and know what the transformations must have been. Again, very similar example, square root function, dilate factor of 2, but we're doing it from the y or along the x. The 2 goes on the x, rearrange, and now we're replacing the x with the x over 2. Once again, we see it appears as a division rather than a multiplication. So when you look at this function here, you say, this therefore has a dilation factor of 2 from the x, or sorry, from the y, excuse me, or along the x. Any questions about that? If I go too fast, just let me know. Happy to go back and answer any questions about older stuff as well. Okay, the next type of transformation is the reflection. This is all about essentially mirroring the coordinate either in either direction, either the horizontal reflection or a vertical reflection. Reflection in the y-axis is going to be your horizontal reflection. The reason why is because the wording is as such as whatever axis is mentioned, you can think of as like a mirror. So what I'll do at this point, I'll get my handwritten notes section up and I'll do a little quick preview of what this sort of thing would look like. So basically, you would have your axis, you would have a point. And if you're reflecting about or in the y-axis, what you're essentially doing is pretending the y-axis is the mirror. And so wherever your point is going to be perfectly reflected on the left-hand side in this case, which is why when you specify the y-axis, you actually get a horizontal reflection. So in other words, it is changing the location of the x variable. So this is some positive x and now becomes some negative x. The y values are consistent the entire time. It's perfectly horizontal, which is why when you go back to the screen share and have a look, when we're applying our negative sign to indicate the reflection, we're going to put it on the x variable. This is another one where you sort of do the opposite to what you normally think. So the negative sign is going to go on the x in this case. All the other steps are exactly the same. Rearrange, substitute. The negative was on the x, so when we sub it in, the negative will still be on the x. In the example that we have here, we're trying to just apply a reflection, nothing else to it. Negative on the x, rearrange, and then the substitution just means every instance of x is going to be replaced with a negative x instead. Not forgetting, of course, that when you have these like indexes, these powers associated, it is just the negative ends up becoming inside that power because it's x that is squared, and so if x is being replaced by negative x, it is now negative x that is being squared. Don't put your negative out here. So using these brackets is pretty nice for in every instance, rather than trying to go ahead and just try to work it out in your head. This little intermediary step of putting brackets around things that you're trying to substitute can be kind of helpful for making sure you don't make any minor algebra mistakes. Reflection in the x-axis, same sort of idea. The x-axis is now thought of as the mirror, and so if we go back to the diagram in the main meeting menu, reflection in the x-axis, x is now the mirror, and so it would do something like this. We'll notice that the y values are consistently changing, whereas the x is constant, right? Doesn't matter where you go along that vertical line, the x is still going to be whatever that positive value is, which now informs why the y variable is going to get the negative sign rather than the x. Back to the screen share, everything's still the same, right? Negative on the y, negative on the y, negative on the y. And whenever you basically have anything that's impacting the y variable, you've got this additional final step of just making sure that the y is back on its own. As far as what that looks like in an example, same function, but this time we're trying to apply our reflection in the x-axis. Hence, the negative is going to go on the y, rearrange, and replace the y with negative y. From there, it's just simple algebra. Divide or multiply by -1 on both sides to get the y back on its own. That's reflections. Any questions about that one so far? Last up. Is that like a thumbs up for a question or a thumbs up all good to move on? All good. Sweet. Last up, translations. So translations are all about literally shifting as if you would imagine grabbing the function and moving it to a different location. You're literally shifting it in either up, down, left, or right, or some combination of the four. First up, we'll look at the horizontal translations. So, as you might expect, horizontal translations, you are applying either a plus or a minus to the x variable, because you're literally changing the x location when you're moving horizontally. We're going to see something that seems a bit weird, because up until this point, you guys have seen many different functions, and it hopefully would have been drilled into you that x minus a value shifts it right, x plus a value shifts it left. What's going to feel a little bit weird is when we identify our initial transformation, we are in fact going to say the new x is equal to the old x plus a. That would in fact shift it right by a. And the reason why is because what you've been taught to handle is what it looks like in a function after all is said and done with the rearranging. And we're going to see exactly why it does do that flip. But for now, just remember that we're talking about things in terms of the physical points themselves. So if you do want to move a point that exists at 1, 1 to the right by, I don't know, 2, you would literally take that x coordinate of 1 and add 2 to it. That's what we're saying here. It's talking about the point rather than the function. The reason why you get to the x minus a that you would be quite familiar with in the functions is because of this second step here, when you rearrange to get the x and y back on their own. Rearranging to get the x variable on its own ends up flipping the sign of this. And so when you go to replace every variable with what it's supposed to be, y equals f of x, the x gets replaced with x minus a. That's a little bit of almost a trivia thing as to why whenever you have x minus a value, that is actually shifting your function to the right direction. As what that looks like in a less typical function, in this case, we're trying to apply a horizontal translation of -5. So you're going to add your -5 or just do, x minus 5, however you want to write that out. Rearrange to get the x and the y back on their own. Oh, question, can I show the dilation steps again? Yeah. I'll just quickly finish up this example and we'll go back to the dilation steps. So this one, we're trying to apply our horizontal translation of -5 units. So it's going to be -5 on the x. Rearrange, you're going to get that x variable on its own, and then every instance of x is now going to be replaced with the x plus 5. So that now says x plus 5, that now says x plus 5. And from here, I've chosen to expand. If you wanted to, you could actually factorize it out. Right? These both have a common factor of x plus 5. You could take that out the front as a common factor. Before I have a look at the dilations again, do we have any questions about how this one's worked out? Okay. Was there anything specific you wanted to have a look at regarding dilations, or did you want me to just sort of do it from the top again? Look at it from the top? Yeah, certainly. So dilations are pretty much all about stretching a function in a particular direction. It's where you are, if you imagine like literally grabbing like the top and bottom of the function and just sort of pulling at it, imagine stretching the thing. So if I drew like maybe an example of what that might look like, let's say we have a quadratic that is quite wide, like this one on the handwritten bit. Dilating it in the, I don't know, let's say the x direction would make it actually even wider. So in other words, ever so slightly, I maybe done a poor example of that, but it's supposed to be like quite a bit shallower there. Oh, I understand what it is. Yeah, okay, cool. So the steps involved are the same as all the other ones we had a look at. The main thing you got to think about is where the multiplier is going. So it is a multiplier rather than an addition or an application of the negative sign. So for dilations from the y, you just got to think of it as the opposites whenever you see the from way of describing things. So whatever the opposite is, if you're using from, you put the dilation factor, the multiplier, on that opposite variable, and then follow the exact same procedure of before, rearrange and substitute. As for how to remember this sort of notation, the thing that I tend to think of in my mind when I'm reading either of those ways of describing things is I imagine a point on my axis, something like this. And if I am dilating along the x-axis, it just means that I'm stretching in that direction along the x. Perfect. Alternatively, if I saw it said from the y, I'd imagine, okay, well, here's my y-axis, and I want to go away from the y. Oh, shit, it's in the x direction. Cool. So because it's going in the x direction, I put my dilation factor on the x itself. Did that clarify what you needed? Last one we didn't look at was the vertical translation. It is the same thing as the horizontal translation, except the variable is of course going to go on the y. We're shifting vertically, and vertical is all about y. We looked earlier about how we did do a plus to move right and we did a minus to move left. Why doesn't the y variable have that same sort of weirdness? Well, we're going to see we essentially get this sort of double flip going on. So, yep, we're trying to shift up by the factor of a. So we're going to take whatever our old y was and add whatever that factor is. That's going to get our new y dash. When we get to step 2 of rearranging to get the x and the y, that's going to become minus now because you've got to get this y back on its own. Subtract a. Finally, whatever function you have, the only thing that's changed here is the y. So y minus a is going to replace that y. It's at this point we realize, oh shit, I've got to get this y back on its own. So plus a to both sides, and suddenly you're going from positive to negative back to positive. That's why the y transformations tend to be more intuitive. They stay as multiplications when they're the dilation factor. They stay as additions when they go up, and they're minus when they go down. It's the x-related stuff that tends to be opposite to what we expect. As for applying it, it's fairly straightforward. Basically, anytime you apply a vertical translation, you're just going to tack on whatever that number is at the very end. So if we want to apply a vertical translation of -2, well, we're just going to take whatever this was and chuck a -2 on the end of it. That's all it ends up ever being. But if we're being diligent with the procedure that I've mentioned, which will be helpful for when we do multiple in a sequence, then it would be a matter of making sure the -2 is applied to the y as a subtraction, rearrange, and then substitute. Y plus 2 is replacing that, and sure enough, the 2 is now going to go onto the other side to make sure we have the y on its own. Those are all the fundamental ones. We've covered dilations, we've covered reflections, we've covered translations. Anything in there from any of those sections that needs more clarification? Because the next thing is going to be putting it all together in a massive, well, relatively bigger sequence. So be sure to let me know. Otherwise, let's crack on with it. Sequence of transformations. So we're going to slightly amend the procedure that we looked at. Beforehand, we were looking at a 3-step thing. Fundamentally, all that I'm saying here that's different is we're going to repeat step 1 a bunch of times. We're going to identify what that transformation is, and then get that little equation that describes what that transformation is. And we repeat the entire thing in order until we've made it to the end. Only then do we move on to the other step 2 and 3 from last time. Now, it's really important to highlight that you need to do these things in the order they are told you. They are told to you in. To highlight that, I've written 2 separate sequences of transformations which have the exact same factors involved: dilation factor 3, dilation factor 3, reflection x, translate, translate. But they're done in different orders. They are the same factors, but when you do them in different orders, what you'll find is that you get different behavior. So let's have a look. Step 1, identify the first transformation in the sequence. So the first transformation was a dilation factor of 3 from the x. We're going away from the x, so in other words, in the y direction, which is why the dilation factor of 3 is going to apply to the y variable. Next, get the next transformation in that sequence. So we just did dilation factor of 3. We're now followed by a reflection in the x-axis. Here's how that actually looks. Wherever you left off with, you now use that as your new starting point. X comma 3y is now the new starting point. So when we apply that reflection in the x-axis, the negative sign doesn't just go like on the y, it goes on the entire y spot. So it's now 3y. As a reminder, reflection in the x-axis, that means the x-axis is the mirror. So in other words, it's the y values that are actually changing vertically across it, which is why that's got the negative sign rather than the x. Then However long your sequence is, you just do all of them. You got 2 more to do. Translate 5 in the positive x, 1 in the positive y. Or in other words, 5 right, 1 up. So we do exactly that. Where we left off was here, so that's where we're going to start for that next one. It was 5 in the positive x and 1 in the positive y. So you take whatever this says, add 5 to it. You take whatever this says, add 1 to it. From here, we now basically just look over here. Essentially, this is our x dash, this is our y dash. This is the new x, this is the new y after everything that we've done to it. So we write exactly that. X dash is that, y dash is that. Before I go any further, this is the part that's probably the most complicated. Is there anything about that sequence that needs more clarification? Even if you just want me to explain it again on the top. Cool. Okay, we have our x dash and our y dash. Now we're basically at the exact same stage that we had left off at on all the other little individual ones. You rearrange to get the x and the y on their own. You can see how this is more involved now. Now both of these need a bit more rearranging to be done. Subtract 5 from both sides here, subtract 1 and divide by -3 for that one. We now have our y and our x, which makes it quite easy to now shove directly into whatever the function is. Some generic y equals f of x, you replace the y with that, you replace the x with that. Last step, making sure, of course, you make sure you get the y back on its own, which is going to mean multiplying both sides by -3 and then adding 1, getting the y on its own. That's what a sequence looks like. So the reason why I've taught it in this particular way, using the point sort of notation, is because it makes doing things in order exceptionally easy. Because all you do is you just go left to right, continuing to add on to where you left off. You do your little bit of rearranging, which, sure, that's maybe a bit annoying, but it's very hard to make an algebra mistake when you do it this sort of way. There is another way of doing it. I think I touch on it in the next document, so that'll be like next week's lesson on how you can do it that way as well. But for now, we'll basically just focus on this. As for the example 2, again, it's going to be the exact same transformations, just in a different order. So we had the +5 and the +1, we had the minus sign, and we had the multiplication of 3. Why is that going to come out to be different? Well, it's got to do with the fact that the order that you do pluses and multiplications in matters quite a bit. So because translations are pluses and minuses, well, first off, we're just going to start with that, right? Translate 5 in the positive x, 1 in the positive y. If we're just starting with basic xy, you're just adding 5 and adding 1. Reflections are multiplications by -1. Now, it's a reflection of the x-axis. Remember from earlier, that means multiplying the y by -1. But it's not just that. It's multiplying whatever's in the entire y spot by that negative. You don't just put the negative on the y, you put it on the entire y coordinate itself. This is the issue. Whenever you have pluses in there or any additional terms, any subsequent multiplications or divisions are going to apply to both terms rather than just the variable itself. Same thing, of course, with the dilation factor of 3. Dilation factor of 3 is going to apply to the entire spot here. It's 3 times all of this. So if we do a quick look and see 2 different outcomes, -3y plus 1, -3 bracket y plus 1, which are very different things. When all is said and done. Well, I guess not too different, but different enough to cause you to lose the mark. All that to say, make sure you do it in the order. And as long as you're following this guide, like, it tells you pretty straightforwardly what to do. Do the first, then the next, then do all of them. That's pretty much it. So before we crack on to do any practices live together, is there anything about any of that that needs further clarification? In the meantime, I'll get some screen grabs of these little summary sheets so you guys can use them as we're as we're doing our live questions. Okay. Let's give these a shot then. Question 3. In each of the following, find the rule under the given translation. So we have the hyperbola. It's going to be translated 2 units in the positive x, 1 unit in the negative y. Now, some of these are going to be quite basic because we're not going to go straight into the full sequence. So if you do want to do shortcuts, feel free. There is a shortcut list in the screen grabs that I've given you. If you want to just use the little like end results. But it could also just be worth making sure you go through the procedure so you know how to do it in the easier way. That way, when it comes to the harder questions, you'll be able to apply it just as well. So 3a, we have f of x is equal to 1 over x. We've got to do a translate of 2 in the positive x, 1 in the negative y. What's that going to look like? Any ideas on how it gets done?
We look at the order of transformations there.
Yep. So what's that going to look like?
So, 2 units in the positive direction of the x-axis. So, translating 2 units, right? So, that's going to be 1 over x minus 2.
Yeah. So if you want to put them directly in there, then yeah, absolutely. You would have 1 over. Where's my? Oh, I've run out of space on this. Nice. Let's create a new page. Over like 2. Yeah, so in function notation using those shortcuts, that is indeed a shift right by 2. Nice. What else?
1 unit in the negative direction of the y-axis. So that's 1 unit down, so the whole function minus 1.
That's it. Yeah, perfect. So the whole function gets the minus 1. So final answer, f of x equals all of that. Nice. Cool. So as far as what we were looking at there, that'll be these little shortcuts at the very end if we look back at the screen share. So horizontal translations, when they're substituted directly into a function, become x minus the value. When vertical ones are substituted directly into a function, you're just tacking it on the very end. Cool. Okay. These are all just going to be translation ones. I'll do maybe 1 or 2 more, and we'll move on to our dilations, reflections. Actually, part B won't be too bad. Yeah, why not? Part B. So same thing, but now we're doing the truncus. F of x is 1 over x squared. So in this case, we have 4 units positive x, 3 units positive y. What's that going to look like?
For units in the positive direction of x-axis, so translate right? So 1 over x minus 4 goes to.
That's it. So every x gets replaced with x minus 4, of course, making sure that because it is x squared, the x minus 4 is all getting squared. Cool. All right.
And change in the positive direction of the y-axis, so change up the whole function plus 3.
That's it. In the function notation, it would look something like that on the left-hand side. 1 over x take 4 all squared and plus 3. Sweet. That's pretty much it. What I really wanted to show there was the substitution, making sure the translation factor gets inside of the square. You'll see all that notation as well in stuff like question 4 and 5. So identifying what those look like in the actual function notation itself is important, which is why I've got the little cheat sheets for those as well. Cool. That's translations. Let's get some dilations going. 2 is a bit of a weird one because what they've done is they've basically given you 4 separate functions and then 6 transformations to apply to each of these. So 6 by 4 amount of questions in there. So I think what we'll do is we'll do y equals x squared and we'll just do I for this one. So a I x squared, and it's going to be a dilation factor of a half from the y. Start writing that up. X squared. Alrighty. Dilate factor of a half from the y. What's that going to now look like? Use the shortcut cheat sheet, or you can use the procedure if you feel like that's easier. Either way. 1 over 2 x squared. The notation, there's no brackets there, so I'm just going to take a stab at what this one is. Is it 1 over 2? Did you want the x squared here or out here instead? It'll be 1 over 2 x squared. There's option 1, there's option 2. Out. So like this. Cool. It's quite cool to do that, yeah. Putting dilation factor of a half, normally we think of that as like a multiplier. What's being said specifically as from the y-axis matters quite a bit. If we look back at the screen share from the y, if we are going to just sort of shove it directly into the function, from the y is this shortcut here. So basically every x is going to be replaced with x divided by a, where a is that factor. The one you've identified as would be from the x or along the y. So yeah, exactly, looking at it along the y, precisely, which is why I know I hate this sort of notation, because you look at the y-axis and you're like, oh yeah, it's just going in the y direction, perfect. And yeah, exactly. It's where all the confusion comes in. So yeah, along versus from. But yeah, so this will just be now x divided by a half. So in other words, we take that quadratic. Let's just erase this real quick. Y equals, now instead of just being x, it's x divided by a half squared, which you can now, of course, do a bit of rearranging here. Quick fire question. Does anyone know what this one simplifies to?
2x. Yeah, 2x all squared.
2x all squared. Perfect. So anything divided by a fraction, you just basically flip it. 2x all squared. And by convention, you'll typically also pull this out as well. Make it 4x squared. Cool. All right, that one. This time we'll do d. We'll do the square root. So y equals root x. And what's a good one to try? We did from the y. Let's do this iv, a dilate factor of 4 from the x. This one I'm going to look at. What was this one going to end up being, rather? Dilate factor of 4.
Y
Hmm?
square root of 4x.
Like this, square root 4x.
Yeah.
Okay. Again, the notation, the way it's described, the key wording of it, of from the x. If we have a look at what that's referring to, from the x is referring to this one here. Yes, so it's going to end up being the 4 root x. Yeah. It's the a at the front of f of x as a full multiplier of it. So in this case, you kind of put it in the middle, which you can actually put it in there, but just not as a 4. You know, you have to use the square root rules to shove it through if you wanted to. Similar to how we squared it on the way out, you'd have to square root it on the way in. It's vice versa here. But yeah, 4 root x would be the more accurate answer there. But yeah, that terminology there, it feels like we should probably practice that a few times then. What axis is being mentioned is going to matter quite a bit. So let's do a few more. This time we'll try that truncus, y equals 1 over x squared, and we'll do triple I on this one. Dilate factor 2/3 from the x. I just noticed you actually put the actual root in there. I didn't even know the keyboard could do that properly. That just went by me. Yeah, fair. Yeah, usually if it's typed, you'll just like literally type out the word root and then put it in brackets. Yeah, fair enough.
This one looks to be the um. It should be the same, isn't it? So
Yeah, the same rule. They're both of them say from the x like we had last time. So yeah, what's that going to mean?
so we just multiply it by the factor.
That's it. Yeah, so it's 2/3 multiplied by 1 over x squared, or, you know, just chuck it through. 2 over 3 x squared. Should probably write that in a not terrible way. Yeah, exactly. Just multiply right through. Nice. Lastly, we'll do the hyperbola. So that'll be y equals 1 over x, and we'll do double I, dilate factor of 5 from the y. One over 5x, so like y equals 1 over 5x like that. Yeah? Okay. So let's have a look. Dilate factor of 5 from the y. If you look back at the screen share, from the y is going to be this one, which means rather than it being a multiplier, it actually ends up being a divider, unfortunately. This one's a bit weirder because it's a fraction and you're shoving in a fraction into that denominator as well. So you actually end up dividing the x by that 5. It's a bit of a strange one. So you're replacing x with x over 5. So rather than having it like that, it ends up coming out to be that, which then flips over. So I'll highlight the difference again. So what we would have would be, so if this was from X, then you would have just the, yeah, if it was from X, if we better have a look at the cheat sheet from X, it's a multiplier of that factor, yeah, on the entire function. So it's 5 times 1 over X, or in other words, 5 over X. If it's from Y, then it's replacing this X with the division of that factor. So 1 over X, where X is now X over 5. Now, funnily enough, for this particular function, they're the exact same thing. Before we explain why they're the same thing for this one, is it fair enough how that little nuance is? We're replacing X with the division of 5 because it's X over A. Is that fair enough? Let me know if not. So, as for why these are the same function, it has a little bit to do with the actual shape of the hyperbola itself. So, all familiar with the hyperbola being like that. Because it's got this sort of symmetry to it, whether you stretch this in the horizontal direction or the vertical direction, you end up doing basically the same sort of thing. It's a bit weird in that way, or at least the math just ends out being like that. It's got this sort of horizontal sort of symmetry to it. So stretching in one direction versus another doesn't tend to actually do a whole lot. But anyway, that's just a bit of trivia for that particular graph. You'll find that common in actually a few graphs, oddly enough, where just by looking at the end result, it's kind of hard to tell whether that was a dilate factor from the Y or from the X. Because the truth of the matter is it can be both. It just depends on what number you say. Can you explain again? I thought 1 over X divided by 5 will be 1 over X times 1 over 5. Times 1 over 5. Yes, that's the issue. You're doing times. Hang on. 1 over X times 1 over 5. I think you're still. Wait, have I just made a mistake here? Dilate factor of 5 from the Y. Let me do this myself. I could have just done a stupid. Because it's replacing X with X divided by 5. So it's 1 divided by X over 5. 1 times 5 over X. Yeah, 5 over X. So I think maybe what you're looking at still is that first dot point where it's A times f of X, whereas what you're trying to do is X over A. You're replacing that X with the division rather than doing multiplication of the fraction. There's two separate ways of going about that. This is the weirdest part, right? When you've got fractions stacked on each other, it can be kind of difficult to see what it ends up looking out to be. So what I tend to do is this, where I literally replace whatever the big one is with a division symbol. That way it's now more obvious how that resolves. Division of a fraction, you flip that fraction, and then it becomes multiplication at the end. Versus if we were to just do multiplication of that factor, it's unfortunately not enough to just flip it and then call it a day. You're kind of combining two things in one, I guess I would have to say. But yeah, I guess just practicing a lot of these, looking at the correct headings of them, and just looking, okay, it's exactly this, so I've got to do exactly that. Is it more looking at the headings of the thing, or is it the algebra itself that's weird? I think the algebra, yeah. Um, oh, actually, I think I know what you mean. Um, because you're thinking 1 over x, and then you're dividing by 5. Um, when it's, yeah, f of x divided by a. So that notation there, if you look at the screen share, that does not say divide your function by a. It says divide the x variable specifically by a. So I think I see what you're thinking, because you're thinking it's 1 over x and then divided by a, which would then become 1 over x times 1 over a, 1 over ax. I think that may be what you were thinking is going to happen. That would be if I said f of x over a. That's what that looks like. Yeah, you see the difference now? Sweet. Okay, cool. Because yeah, these things are complicated, right? The notation, there's so many different little notations there. I mean, if we look at the sheer number of transformations we just looked at, 1, 2, 3, 4, 5, 6. There's 6 separate little things on how to do it, and if you're doing the point stuff, 6 more things to have a look at as well. So transformations is notoriously one of the toughest subjects in one of the toughest topics in methods, and it's little shit like this, which is why. But yeah, hopefully that clarifies things a bit further. Cool. Okay. Yeah, no worries. Happy to help. Because these little things, even outside of transformations, actually understanding the notation of what this actually looks like, you see it all the time, especially in like your extended response tech active SACs exams rather. They'll chuck that sort of notation to you, so it's really good to know what that ends up looking like. Okay, I guess that's about it for the fundamental ones there. We didn't do reflections actually. We haven't got we've got about 5 minutes left or so. Do we want to do the reflections on their individual little examples, or do we want to have a look and see if we can do at least one combination or sequence of transformations together? I can do either here. Reflections? Yeah, sure. Let's do it. So let's go with yeah, why not? We'll go the quadratic. Y equals x squared, and we're going to try and do v, the reflection in the x-axis. You're using the screen share, it's kind of split across um, two separate ones. It's the whole reflection section is in the second screen grab, in the Y versus in the X. One of the other things you can think of actually is also if you know what the graph is going to look like what the original graph looks like, you can kind of just use your own understanding of what the function should be to do these. I'll let you guys have a stab at guessing it first, but then I'll show you this sort of graphical approach. Yeah, negative x squared, exactly right. So it was a reflection in the x-axis. So we look at the spot that says in the x. We see that it's a negative sign on the entire function itself as a multiplier at the end, or at the beginning, I guess. So we're going to do exactly that. Y equals negative x squared. Sweet. What I was sort of rambling on about in the middle of that was, if you think about the quadratic itself, we know it looks like this, basically. And a reflection in the x-axis, as long as you know that means that you're doing this, you're flipping it downwards, then even if you don't really know exactly what that would look like in the rule, what you can do is just draw what you imagine that to look like, the flip downwards, and then look at this and be like, oh shit, that's just negative x squared. I know what that one is. And so you can use these sorts of things to try and figure out, okay, what does this actually look like in the rule? What does this actually look like in the function? We're going to do the quadratic again, but this time we're going to do the reflection in the y-axis. And I've picked the quadratic for a very particular reason here. Y equals x squared, reflection in the y-axis. Bit of a cheeky one. Yep.
And say the same.
Yeah, it's going to be the exact same thing, isn't it? Y equals x squared now flips to y equals x squared. If we look at where the reflection should go, it should go on the x specifically. But because it's squared, it goes inside the square, which, well, when you've got a negative squared, disappears. So that's the algebra reason as to why it sort of cancels itself out. You can also just look at the original graph and notice that, hang on a minute, this is already symmetrical about the y-axis. If I were to try and flip it about the y, I get the exact same thing no matter what. We're squaring any negative to make it positive. But yeah, again, this is the duality between knowing the algebra behind the things and also just knowing what the graph looks like. If you're more familiar with what the graph looks like, maybe you start there and then try to picture, okay, well, nothing's actually going to change here, so it's just going to be x squared again. Or if you prefer the algebra, you probably start there. Now, ideally, you should be good at both. We need to get you good at both. But when you're starting out with these sorts of things, absolutely, just take a look at the guides that I've got here. Literally just do it step by step. Mainly, I guess, use these shortcuts for the first, like, 7a, 7b. 7c, when you start doing a whole bunch of them, you can still use the shortcuts, but just making sure you definitely do them in order. But I see it all the time that students will do things in the wrong order by accident. So having this sort of step-by-step sequence with x dashes and y dashes, I've seen tends to have less error in it. It just means it's a little bit slower, but acceptable when you're starting out. That's about it. We've hit time on that. I'm happy to stick around for a little bit if there's anything further to clarify on any of those concepts. Otherwise, I'll let you guys enjoy the rest of your day. Got class tomorrow, which will be the Unit 3-4 related stuff. Continuing on with integration. All right, take care.
Hey, can I ask you something about my classes?
Yeah, certainly.